Bam! Mr. Tarrou, in this calculus lesson, we are going to be introduced to something called a Taylor polynomial and use it for approximations. It's very, very interesting. It's very cool. We get to create a polynomial, just a function who has one independent variable and all of the powers or exponents in that equation. That function is a positive integer, and we're going to be able to use that to estimate cosine functions, natural exponential functions, natural logarithmic functions, or any logarithmic function for that matter. And we're going to be estimating these functions around a particular center. Now, as we go through this lesson, you might be going, why am I creating, even though it's an interesting and cool concept, why am I creating what may seem like a very complex polynomial, to estimate something that I could just put in my calculator? Like, we're going to estimate the cosine of 0.7 with a Taylor polynomial who's centered around pi over 3. Well, in the olden days, they didn't have calculators. We didn't all have phones, supercomputers in our pocket that did, everything. And it does have uses later on as you go through your studies of calculus and later math classes afterwards. So everything will come back and have its purpose repeatedly later on as we continue our journey through mathematics. So, your Taylor polynomial, well, the nth Taylor polynomial and the nth Maclaurin polynomial is if we say that if f has n derivatives at a particular center C, then the polynomial centered around C is p sub n of x, and that subscript is just going to be that nth degree, or you're looking for the third, fourth, fifth nth degree. And as we increase these nth degrees of the polynomials, we're going to get better and better approximations of some other function around a particular value. And what I'm going to do before we move on to, or after we set up this third degree Taylor polynomial, is I'm going to display this cosine function, and then I'm going to display the first, the second, and the third degree Taylor polynomials. So you can see how, just visually, you can see how these polynomials are in increasing steps of, 1, 2, and 3, that is estimating and following that cosine function. And we have f of c, so we're going to put the center where we intend to make the center of our Taylor polynomial into our original function, and then we're going to work with the first derivative, f prime of c times times x minus c, and then plus, we're going to move on to the second derivative, still plug in the center of our center value, the center of our Taylor polynomial in there, and have it multiplied by x minus c squared over 2 factorial, plus the third derivative with the c plugged in, f triple derivative, triple prime, 3 primes, third derivative of f of c times x minus c to the third power, and then over the third factorial, the next term will be the the fourth derivative, fourth power over the fourth factorial, so on until we get to the nth derivative of f of c times x minus c to the n power over n factorial. And we're going to, in a couple of sections, at least in the textbook that I'm using for my classroom, ultimately have this turn into a series. Right now, we have sort of a partial series, and we're going to stop at some degree and make an estimation. And through the video, we are going to be talking about, well, what's the remainder? What's the maximum possible error that we're getting from our Taylor approximation, our Taylor polynomial approximation. Now, if c is equal to 0, you have an nth Maclaurin polynomial. So Maclaurin polynomial is just a special type of Taylor polynomial. These are used, I already said this, but these are used to estimate the value of another function at x when centered around c. So as you look at this notation, once you create this Taylor polynomial and you use it to make an approximation, it's an approximation at x with c being the center of our Taylor polynomial. And with the computer graphics you see up here after we set up our first example, you'll see what I'm talking about with that idea of center. Find the third Taylor polynomial for f of x of cosine of x. We're going to make a polynomial that estimates the cosine function around the point pi over 3. So let's see here. We want a third degree Taylor polynomial. So we need to recognize what the function is itself. We've got that f of x is equal to cosine of x, and we need to work out what the first and the second and the third derivatives are. So we have f prime of x Well, the derivative of cosine is negative sine. F double prime of x, the derivative of sine is cosine, so we have negative cosine of x, and f third derivative of f of x. Again, the derivative of cosine is negative sine, so we're back to positive sine of x. This formula is asking for, oh, and you can find a proof for this Taylor polynomial, the definition of a Taylor polynomial in the back of your textbook, or you can look it up online. I'm just going to work through these problems. We're looking at finding the values of these derivatives until you get to whatever the nth Taylor polynomial you're looking for. So let's go ahead and plug in f of c, f prime of c, f double prime of c, and f triple prime of c. So we can plug them into our formula. And again, we're using that center value of pi over 3. Okay, so since we're just going to the third degree Taylor polynomial, we're just going to start plugging in these values and write this out. So we're going to say p of our Taylor polynomial to the third degree, if you will, of x is equal to f of c. So we're looking at 1/2, and then plus the first derivative. Well, that's negative, so we're actually going to write minus square root of 3 over 2 times x minus c. So x minus pi over 3. Now, we're using the first derivative, so we're talking about the first power, and it's over 1 factorial, which isn't written in the definition of a Taylor polynomial, but to make sure that you probably already see this pattern, but first derivative, 1 prime factorial, second derivative, second factorial, third derivative, third factorial, nth derivative, nth factorial. So we have f of c minus f prime of c, x minus c to the first power over 1 factorial. Now we're going to work with that second derivative. Again, it's negative, so minus 1/2 times x minus c to the second power and the 2 factorial. And now we've got our third derivative, so we're looking, and it's positive, so we're looking at plus square root of 3 over 2 x minus pi over 3, third power, over 3 factorial. And this is going to clean up to be our third Taylor polynomial centered at pi over 3. We got 1/2 minus square root of 3 over 2, x minus pi over 3 to the first. Now 2 times 1 is 2 times 2 is 4, so minus 1/4 x minus pi over 3 squared. 3 times 2 times 1 is 6, 6 times 2 is 12. And voila, our third degree Taylor polynomial centered about pi over 3. We're going to use that now in a minute to estimate the cosine of 0.7. An estimation that is going to have a very, surprisingly, for only a third degree polynomial, and this function, which is curving, the cosine function, which is curving as a wave and all over the place, you get a really surprising estimation. And of course, this is a much more complex looking equation than just a simple cosine, but if I don't have a computer or calculator which again, modern times seems like that's kind of very unlikely, but you could really work this out with a simple 4-function calculator where you would need a scientific or graphing calculator to work out what the cosine of 0.7 radians is. Now, before we move on to that, let's see what that cosine function, the first, the second, and the third degree Taylor polynomial centered around pi over 3 looks like, so you can see how these are estimating, in this particular case, the cosine function. So here we have our T-Inspire graphing calculator up, and y equals the cosine of x displayed in radian, of course. We're going to double tap this and open up our menu here. And this is the first degree Taylor polynomial centered around pi over 3. If we display that, we see that we have a linear function and it is touching, intersecting the center of that Taylor polynomial is at pi over 3. And it's not a bad approximation. Clearly it's a secant line. If we take this off though and show the second degree Taylor polynomial, and we know this is the second degree because we have f of c here. We have a first derivative, and we can see the power is equal to 1 on our x minus c factor. Now, this is in simplified form, so you don't see the 1 and the 2 factorial down here, but we see our x minus c has a power of 1 and a power of 2. So this is our second degree Taylor polynomial, and you can see the x minus c centered around pi over 3. And all of a sudden, we've got this black graph coming through, and it really seems to be almost touching, sharing that cosine function for a much longer interval of domain. And there's errors along this, of course. We're going to talk about that through the lesson. But it does seem to track that cosine function better than our linear first degree Taylor polynomial did. Now, if we turn off the second degree Taylor polynomial and go to the third, which is what we're going to work with through the rest of our example, look at that. Look how closely this third degree Taylor polynomial centered around somewhere in here pi over 3 is tracking our cosine function. So we can see that obviously the estimations that we get from its third degree Taylor polynomial is going to be much better than the first or the second. Now, let's get back on to our example. So we have the Taylor polynomial, which we're going to use to estimate f of x is equal to the cosine of x, centered about pi over 3, is, as we just calculated in the previous example, this. And we want to use that to estimate the cosine of 0.7. So that means that we're basically going to plug 0.7 in here everywhere that we see an x, and just simply then use maybe a simpler type of calculator to estimate the cosine of 0.7 without the need of a scientific or graphing calculator. And it's going to look like this. And that estimation, right off the top of my head, comes out to approximately 0.7645. Now I do say approximately. That's not the exact answer. Now we can type this into our calculator and see that actually with our fancy calculators that the cosine of 0.7 should be equal to 0.7648. So with just a little bit of work, now granted, this wouldn't need to be with a simpler calculator, we could estimate that cosine of 0.7 within 0.0003. So really, really close approximation with just a third degree Taylor polynomial. So we can see that these estimations, as we could see by those graphics that we were looking at with our graphing calculator, that this estimation is quite good. And you need to be within that some neighborhood of pi over 3, the center of a Taylor polynomial. But if you're somewhere within a reasonable range of that center, we get very, very good approximations. Now, but going with that idea that this is about needing to estimate and make approximations, we have this other thing here. We have some kind of Lagrange form of the remainder. We can look at analyzing what would have been or what is the possible maximum error that we could possibly get when estimating the cosine of 0.7 with this third degree Taylor polynomial when it's centered around pi over 3. What's the maximum possible error? So we can say, hey, look, if we do this estimation, we can be actually more accurate, because this is the maximum possible error. We can be within this or even less in terms of error, or be within this or even with more accuracy with our approximation. Use the Taylor's theorem to obtain an upper bound for the error of the approximation. Well, Taylor's theorem. Taylor's theorem says that we have f of x is equal to f of c plus f prime of c times x minus c. We're just seeing that definition that we saw on the previous screen, but now we're adding this extra term at the end, r sub n of x, the remainder, the error. Now the error is actually the absolute value of r sub n of x, but the remainder is equal to, that Lagrange form of the remainder, r sub n of x is equal to f to the or the n plus 1 derivative of f of, now all of a sudden this other variable of z pops in, which you may very well see in your textbook. It's not in every textbook. I did some research because as I was prepping this lesson and making these Calculus 2 videos for you guys, and hopefully maybe someday be able to teach at my high school, I really did not understand where the c came from, or the z value came from. So every book uses different notations, but I finally got it cleared up, and here we go. We have the n plus 1 derivative of f of z over n plus 1 factorial times x minus c to the n plus 1 power. So we're really just taking this, this function, the first, the second, the third term, if you will, the third derivative and the third power, and we're just moving one step forward. So we're going to keep counting that up by 1. So that's where we're getting the n plus 1. We're just going one term beyond that sort of nth term, if you will, that nth derivative, nth power term, and doing the n plus 1 derivative and n plus 1 power, that next term in this polynomial. Now, I don't have it written up here, but we're going to be talking about Taylor's series in a couple of sections, the way it's laid out in my textbook I'm using to prep for these videos. And if the limit as n approaches infinity, if you can write out this Lagrange form of the remainder and prove that as n goes to infinity, this approaches 0, you're actually showing that you can represent a function, and not just with a Taylor polynomial, but actually with a Taylor series or a Maclaurin series that would estimate exactly this function at any point you would like. So C, like we've already seen through the graphics on the graphing calculator, is the center of our Taylor polynomial. X is where you want to estimate this function with the Taylor polynomial. And Z is going to be on the closed interval, and I just wrote this twice because we don't really know what's going to be smaller, C or X, but Z is on that closed interval, and it makes, you're looking for that Z that makes the greatest possible error. You want to, if you're going to make an estimation, you don't want your estimation to be farther off than predicted. If it's more accurate, that's okay, but it cannot be less accurate. So you want to choose that Z such that when you plug it into the n plus 1 derivative, because it's in the numerator, you want that to be the largest value possible to show what the greatest value the error can possibly be. And then if you're more accurate, that is okay. So we're going to step off, we're going to clean this up a little bit, and we're going to show how to figure out the math for finding the largest possible error. What can we expect to see as our largest possible error if we're estimating the cosine at 0.7 when it's centered around pi over 3? And we're going to have a little bit of a footnote in this, and I'm just going to reveal the solution to make sure it's all nice and neat and I don't write something stupid incorrectly for you guys using this as a lesson. Yes, I learned this in college. I have a math degree, but that was 25 years ago. And I'm trying to relearn this to present it to you all and use it hopefully in my teaching through the years, through tutoring, through hopefully at my high school at some point, so on and so on. And for you guys, calculating the maximum error for these trig functions, there's a little bit of a funny twist. And I'm noticing the solutions guides that go with my book become less and less of a solution guide and more of just like an answer list as I delve and work my way farther through the book, and I had a really hard time trying to figure out how I was going to explain to you guys the little bit of a twist that is in this problem, and you'll see the same twist and it's consistent. I finally found a textbook that gave a good way of explaining this. Where did they get the value from to put in for the the n plus 1 derivative of f of z, what some books call simply just capital M, the maximum error. So we're going to see that right now. So here we go. You saw me reveal this. Just a reminder that our c is pi over 3. We're going to be, we estimated that cosine function at 0.7, and z, therefore, is going to be on that closed interval from 0.7 to pi over 3. And we had that f of c, f prime, or that term with the power and the factorial of 1, the powers, the derivatives, the factorials of 2, 3, and then the remainder that's based on the third degree, in this case, Taylor polynomial. But, right, that's really one more term in this. Ultimately, what we're going to be building up to into is a Taylor and Maclaurin series. So those powers are going up. Those powers, or the powers, the derivatives, the factorials are going up by 1. So even though this says that the maximum error is the absolute value of the remainder, we have a subscript of 3. We see the derivative, the power, and the factorial of 4, just adding that 1 in there. Now, as I was doing the homework and preparing the notes for this video lesson, I saw all these examples in the textbook and the solutions that showed checking, whatever that, in this case, it's the fourth derivative, checking that nth derivative at the endpoints of this interval. And when I did that with, in this case, well, I made this example just for the video, but say if this were the textbook problem, and I was testing that with 0.7 and pi over 3, even though it was different numbers, I was not getting the 1 that I saw them showing in the solutions guide. And the example in the book that I use had a 1 there as well, but they didn't quite say it so eloquently that I saw this in another textbook. It basically said, hey, look, remember, we're trying to find the maximum possible error. It's okay if our actual error is under that, but just not over. So they say I'm saying this, for most questions you'll be checking for the maximized error on that closed interval, the endpoints. But since f of the n plus 1 derivative of f of x, and you saw in the first pages of us starting this problem, those derivatives alternated between a positive negative sign and positive negative cosine. You saw that in our example. So we know that the absolute value of the n plus 1 derivative of z is going to be guaranteed to be less than or equal to 1. So it's basically out of convenience for all x. And the z is just an x, if you will, on that closed interval. So that derivative value is never going to give us, the absolute value of that derivative is never going to give us a value that's greater than 1. So we just basically set it to be our maximum, our z, or n plus 1 derivative of f of z is just, we're going to just take it as an m value of 1. This capital M is like a maximized error. The error value is not 1, but another textbook uses a little bit different notation and they used a capital M. So in case you're seeing like capital M to determine what goes here as our first factor in the numerator, and I'm saying that it's, some kind of derivative of f of z, different books, different notation. But anyway, any of these Taylor inequalities. So our maximum possible error, and we were under that when you subtracted the calculator value with our estimated value, but the error that we will get will be guaranteed to be under 0.00061. Now, what do you do? And I kind of do this in statistics. I teach AP stats as well. Like, if you want to be within a certain amount of error, in statistics, we would want to say, like, if you want the margin of error to be under something with a certain level of confidence, if you want to guarantee that your maximum error is under a given value, how do you calculate to what degree you take that Taylor or Maclaurin polynomial to? That is our next example. So we're going to determine the degree of the Maclaurin/Taylor polynomial required for the error in the approximation of the function, that cosine function, at the indicated value of x to be less than 0.0001. So again, we're building this whole lesson around f of x is equal to the cosine of x. Our c was pi over 3, and our x is 0.7, and that z is the value on the closed interval from 0.7 to pi over 3 that maximizes that error. So our maximum error, the error which is the absolute value of the remainder. Okay, so that Lagrange Lagrange form of the remainder is f, the n plus, I keep wanting to say f first, but the n plus 1 derivative of f at z times x minus c, which is our pi over 3. Well, actually, let's just write the formula out. C to the n plus 1 power over n plus 1 factorial, absolute value of that. Now we want that to be less than or equal to, actually, excuse me, we want our remainder, our maximum possible error, to be less than or equal to this value that we're getting from the Lagrange form of the remainder, and that is to be equal to, well, we want our remainder, our error in the approximation, to be less than or equal to 0.0001. Now, we're building this off of what I struggled with the most in the beginning, not so much because cosine or sine is so difficult, but where they got that one value that they came from and the maximized value. So we have, this is, as footnoted in the previous board, this f to the n plus 1 derivative of f of z we've accepted to be a maximum value of 1 times our x, which is, again, 0.7, minus our c of pi over 3 to the n plus 1 power over n plus 1 factorial. Now, really what we're doing here is we're just trying to figure out I wrote equal to, but I really want that to be right. We really want that to be less than or equal to as far as what n value we want. And really at this point, I just wanted to let you see the notation and the process you're going to go through, but you're just going to do trial and error with this. Start plugging in n values of 1, 2, 3, and 4 into this expression 5 and so on, and just do a little bit of trial and error until you see a maximized error, which is really, it said equal to, but it's really, you're looking for an error that's equal to or less than 0.0001. And as you plug in the values of n of 1, 2, and really you don't even need to try values of 1, 2, and 3, because we saw our maximum error in the previous screen of 0.0006 something, right? So we already know we have to go up to 4 and 5 and 6, but as soon as you put in an n value of 4, this expression is going to give us a maximum error which is less than 0.001. So you just do a little bit of trial and error, and you say by trial and error, we get n has to be equal to 4. Now n can be greater than 4, but why do more work than you need to? If you use an n of 4, if you use a fourth degree Taylor polynomial, you're guaranteed to have an error that is less than 0.0001, and that's how you determine how much work you need to do to set up your Taylor polynomial. Now, our last example, I wanted to build this whole thing around one function. We now know how to set up a Taylor polynomial. We know how to do it around, really, I didn't do a Maclaurin polynomial, but that just means c is equal to 0. I'm going to display here a problem that says approximate the function using a third degree Taylor polynomial. That function is going to be f of x is equal to the natural log of x. We're going to estimate its value at 2.2, and then we're going to calculate what is the maximum error that we could expect from that estimation. We've already covered all of this, so I'm going to just step off, display the problem. I would suggest pausing the video, make sure that you can use your notes to work through this problem. And I'm just going to come back and finish up the video. This is just a practice problem. I'm just adding this in to give you some more examples, more practice before you start your homework. Bam! Right? So we were asked to set up a third degree Taylor polynomial. We were asked what the upper bound of the error of this approximation was. So because we were asked about the upper bound for the error of our approximation, when I went down my list and I was working with my derivatives, I went ahead and went all the way to the fourth derivative because, well, that remainder is that next term in that addition. So yes, we're using a third degree Taylor polynomial, but we need that fourth degree to calculate, as you saw, the maximum possible error. We centered around 2 because 2 was close to 2.2, and thinking about the idea that this, being an estimation, maybe we know what well, we know what the natural log of 1 is at 0, but the natural log of 2, the natural log of 3, there's like some standard values maybe that we have in a table, and we're going to use those to build off and estimate that function somewhere else. Just sort of like, where did that center of 2 come from? After finding that first, second, third, and fourth derivative, we found that the function's value and those derivatives around that center of 2, plugged it into the formula, did a little bit of cleaning up, and we got an estimation that the natural log of 2.2, based on what we know, where it is equal to at 2, the natural log of 2, we got that approximation of 0.78848. Now, again, thinking of the idea that this is all approximation, how close, at a maximum, how far off is this estimation? So the remainder from this third degree Taylor polynomial is that fourth derivative of z times x minus c to the fourth power over 4 factorial. And in this case, we don't have that function of that natural log function bouncing back and forth between just -1 and 1 and having an easy maximum value to pick, and plus the natural log function's not alternating. I'm using that fourth derivative, and I'm checking the fourth derivative at the endpoints of our interval at 2 and at 2.2. And I'm going to use, now of course, got to think about absolute values here. Negative 3.75 is not truly larger than negative 0.256, of course, but it's negative, it's actually smaller, but in terms of absolute values, it is going to give the largest possible maximum error, and we are guaranteed that this number is no more than 0.000025 away from the actual value. I missed a true? Bam! Go do that calculus homework.